Block 1. Chien-Shiung Wu Introduction. Hello, and welcome to our deep dive into the stories that science history sometimes forgets. Today, we're peeling back the layers on a moment that not only shattered a fundamental law of physics, but also exposed a deep-seated injustice at the very pinnacle of scientific achievement. We're talking about a woman whose name should be as famous as Marie Curie or Albert Einstein, yet for many remains in the shadows. Her name is Chien-Shiung Wu, a titan of experimental physics, and this is the story of how she proved the universe itself is not impartial. Before we can appreciate the earthquake she caused, we need to understand the world she lived in. Not just the social world of the 1950s, but the world of physics. For decades, physicists operated under a beautifully simple and elegant assumption called the law of conservation of parity. It sounds complex, but the core idea is surprisingly intuitive. Imagine you're looking at the world in a mirror. The law of parity stated that the reflection of any physical process, any interaction between particles, is also a possible physical process. In essence, it claimed that the laws of nature are perfectly ambidextrous. There is no fundamental difference between left and right. If you watched a video of a billiard ball collision and then watched a mirror image of that same video, you wouldn't be able to tell which was the original and which was the reflection. Nature, it was believed, had no preferred handedness. This wasn't just a casual idea, it was a cornerstone of quantum mechanics, a symmetry that physicists trusted implicitly. It had been tested and held true for gravity and for the powerful electromagnetic force that governs light and electricity. It was considered a sacred, unbreakable rule. Now, let's meet our protagonist. Chien-Shiung Wu was born in a small town near Shanghai in 1912. Her father, a passionate advocate for women's education, founded a school for girls which she attended. From her earliest days, she was encouraged to be brilliant, to be curious, and to shatter expectations. Her academic prowess was undeniable, and she excelled, eventually graduating at the top of her class from the National Central University in Nanjing. But her ambition was bigger than the opportunities available to her at home. In 1936, she sailed for America, enrolling at the University of California, Berkeley, a global hub for physics. There, under the mentorship of titans like Ernest Lawrence, the inventor of the cyclotron, she honed her skills. Her reputation grew rapidly. She was known for her meticulousness, her precision, and her sheer genius in the laboratory. Her experiments weren't just good, they were works of art, elegant and definitive. During World War II, her expertise was so crucial that she was recruited for the top-secret Manhattan Project, where she helped develop the process for separating uranium isotopes, a critical step in building the atomic bomb. This wasn't a scientist working in obscurity. This was a world-class physicist at the very heart of the most advanced scientific endeavors of her time. After the war, she joined the faculty at Columbia University, focusing on a phenomenon called beta decay. This is where our story truly begins to pivot. Beta decay is a type of radioactivity where a neutron in an atom's nucleus transforms into a proton, spitting out an electron in the process. It's governed by one of the four fundamental forces of nature, the weak nuclear force. While gravity holds planets in orbit and electromagnetism gives us light, the weak force operates at the subatomic level, driving processes like the fusion that powers the sun. By the early 1950s, a strange anomaly had appeared in particle physics, a puzzle known as the theta-tau puzzle. Physicists were observing two different particles that seemed identical in every measurable way: mass, charge, spin, yet they decayed into a different number of smaller particles. According to the law of parity, this should have been impossible. They had to be different particles, but the evidence suggested they were one and the same. This is where two brilliant young theoretical physicists, Tsung-Dao and Chen-Ning, entered the picture. Working at Columbia, they knew of Wu's formidable reputation. In 1956, they took a bold, almost heretical step. They published a paper suggesting a radical solution to the theta-tau puzzle. What if the law of parity, this sacred cow of physics, was simply wrong? What if it applied to gravity and electromagnetism, but not to the weak nuclear force? It was an audacious theory, a shot in the dark. And a theory, no matter how elegant, is just an idea without experimental proof. Li and Yang knew this. They knew they needed an experimentalist of unparalleled skill to test their hypothesis. They needed someone who could design and execute an experiment so precise, so unambiguous, that it could challenge a 30-year-old law of nature. They needed the best. They went to Chien-Shiung Wu. The stage was now set for one of the most pivotal experiments in the history of science, an experiment that would fall squarely on her shoulders. She was about to look into nature's mirror and see if it was telling the truth. Block 2. The Wu Experiment Explained. When Li and Yang approached Chien-Shiung Wu with their radical idea, many top physicists were skeptical. Wolfgang Pauli, another giant of the field, famously bet that the idea was preposterous. But Wu saw the profound importance of the question. She understood that if parity violation were real, it would fundamentally change our understanding of the universe. She immediately recognized the challenge and, with her characteristic determination, abandoned a planned trip to China to dedicate herself entirely to this monumental task. She knew that designing this experiment would push the boundaries of what was technologically possible. The challenge was to isolate a weak nuclear interaction and observe it in a way that could reveal any left-right asymmetry. This is far easier said than done. At room temperature, atoms are a chaotic mess, jiggling and spinning randomly due to thermal energy. Trying to observe a subtle directional preference in that chaos would be like trying to hear a single whisper in the middle of a roaring stadium. Wu needed to create an environment of almost perfect order. Her chosen subject was an isotope called cobalt-60. She chose it for two key reasons. It undergoes beta decay, the very process governed by the weak force she needed to study, and its nucleus has a property called spin, like a tiny spinning top. Her plan was ingenious in its logic. First, she had to get all the cobalt-60 nuclei to stop their random thermal jiggling. This required cooling them to an astonishingly low temperature, just a fraction of a degree above absolute zero, the theoretical point where all atomic motion ceases. This is the realm of cryogenics, and for this she needed specialized equipment and expertise. So, she formed a collaboration with a team at the National Bureau of Standards in Washington, D.C., who were experts in low-temperature physics. The setup was a complex marvel of 1950s technology. A series of nested vacuum flasks containing liquid nitrogen and liquid helium to bring the sample to an incredible 0.01 Kelvin. With the atoms now held nearly still, the next step was to get them all pointing in the same direction. She used a powerful magnetic field to align the spin of every single cobalt-60 nucleus. Imagine millions upon millions of microscopic spinning tops, all perfectly lined up, all spinning in unison. This created the ordered, pristine starting condition she needed. Now, with the atoms cooled and aligned, the crucial observation could begin. As the cobalt-60 nuclei underwent beta decay, they would emit electrons. The question that would rewrite physics was simple. Where would those electrons go? If the law of parity held true, the electrons should be emitted equally in all directions. There should be no preference for up versus down relative to the direction of the nuclear spin. The universe, being ambidextrous, shouldn't care. It would be like a perfectly balanced sprinkler casting water out evenly all around. To detect the electrons, Wu placed a Geiger counter above the aligned sample. The experiment began in late 1956, running day and night. The tension was immense. Wu and her team watched the data trickle in. The Geiger counter clicked, counting the electrons. At first, the results looked symmetrical. But as the sample slowly began to warm up over a period of minutes and the nuclei started to lose their perfect alignment, a pattern began to emerge. A shocking, undeniable pattern. Key visual phrase: the vast majority of the electrons were being emitted in one specific direction. The vast majority of the electrons were being emitted in one specific direction, preferentially from one pole of the spinning nuclei. It wasn't a 50-50 split. It wasn't random. It was a clear, unambiguous signal. Nature had a preference. It was as if the universe was left-handed. Imagine that sprinkler again, but this time, almost all the water shoots out of one side. That's what Wu was seeing. The mirror universe was not the same. The reflection of this experiment would show electrons flying out the opposite way, a result that simply didn't happen in our reality. The law of parity was shattered. The moment of realization in the lab must have been electric. The data was irrefutable. Wu, ever the meticulous scientist, had her team double-check everything. They recalibrated the instruments, they checked for magnetic interference, they tried to find any possible flaw in their setup. But there was none. The result held. On January 9, 1957, after confirming the results with her colleagues at Columbia, the discovery was made public. The world of physics was turned on its head. Wolfgang Pauli, who had bet against the result, wrote in a letter, "I am shocked. I do not believe that the Lord is a weak left-hander." But the evidence was undeniable. Chien-Shiung Wu, through sheer experimental brilliance, had forced a complete rewrite of the fundamental laws of the cosmos. She had asked nature a direct question, and it had answered in a way no one truly expected. The Wu experiment, as it came to be known, wasn't just a confirmation of a theory. It was a landmark discovery in its own right, a testament to the power of careful, ingenious experimentation to reveal the deepest truths of our universe. Universe. Block 3. Nobel Prize in Justice. The fallout from the Wu experiment was immediate and seismic. The news spread like wildfire through the global physics community. It was the talk of every university department, a stunning revelation that sent theorists scrambling back to their blackboards. The elegant, symmetrical universe they had envisioned was suddenly revealed to have a strange built-in bias. It was a paradigm shift of the highest order. The discovery of parity violation didn't just solve the theta-tau puzzle. It opened up entirely new avenues of research and was a crucial step toward the development of what we now call the standard model of particle physics, our current best description of the universe's fundamental building blocks and forces. The importance of this discovery cannot be overstated. It was, without question, a Nobel-worthy breakthrough. And the Nobel Committee agreed. In the autumn of 1957, less than a year after the experiment's results were announced, the Nobel Prize in Physics was awarded for the discovery of parity violation. The recipients were Tsung-Dao Lee and Chen-Ning Yang, the two theoretical physicists who had first proposed the audacious idea. And Chien-Shiung Wu? Her name was nowhere to be found. The very person whose experiment provided the crucial, undeniable proof, the linchpin upon which the entire discovery rested, was completely overlooked. The Nobel Prize can be shared by up to 3 people. There was room. Yet the committee chose to honor only the theorists, relegating the experimentalist who turned their hypothesis into fact to a footnote. The decision sent ripples of shock and dismay through many in the scientific community. It remains one of the most debated and criticized snubs in the history of the Nobel Prize. So why did it happen? The reasons are likely a complex and uncomfortable mix of factors. There has long been a perceived bias in the Nobel selection process favoring theoretical work over the often messy, difficult, and brilliant experimental work that validates it. But it's impossible to ignore the context of the era. In the 1950s, physics was an overwhelmingly male-dominated field. The idea of a woman leading such a groundbreaking experiment was an anomaly, and conscious or unconscious biases almost certainly played a role. Wu herself felt the sting of this exclusion deeply. Though she rarely spoke of it publicly, her private correspondence and the accounts of her friends and family reveal a profound sense of hurt and injustice. Her son later recalled that his mother felt her work had been used to get the prize for others. In a rare public comment, she once said with dignified understatement, "I don't know why my name was not on it." But Chien-Shiung Wu was not defined by the prize she didn't win. Her response to this slight was to pour herself even more into her work, cementing her legacy through an avalanche of further scientific contributions. Her career after 1957 was nothing short of spectacular. She conducted a series of follow-up experiments that further illuminated the nature of the weak force. She made significant contributions to medical physics, including research into the molecular changes in hemoglobin associated with sickle cell anemia. She became the first woman to be elected president of the American Physical Society, a testament to the immense respect she commanded from her peers. She was a dedicated and inspiring teacher and mentor, particularly for young women aspiring to careers in science, using her platform to advocate for gender equality in the field. She was showered with other prestigious awards, including the inaugural Wolf Prize in Physics in 1978, often considered second only to the Nobel. Her legacy is not one of bitterness, but of brilliance and resilience. She is remembered as the First Lady of Physics, the Queen of Nuclear Research. Her experiment is taught in every advanced physics course as a masterclass in scientific method and a turning point in our understanding of the universe. While the Nobel Committee failed to give her the recognition she so clearly deserved in 1957, history has delivered a different verdict. The Wu experiment stands as an immortal monument to her genius. It serves as a powerful reminder that while prizes and accolades are important, the true legacy of a scientist is the truth they uncover. Chien-Shiung Wu looked at a fundamental law of the universe, dared to question it, and, through her unparalleled skill, revealed that it was broken. She showed us a deeper, stranger, and more interesting reality than we had ever imagined. If you found this story of a forgotten genius compelling, please give this video a like and subscribe to our channel for more untold stories from the history of science. And let us know in the comments, what other overlooked scientists do you think deserve to have their story told? Thanks for watching.